just to finish this part, and then next week we start on thin airfoil theory. I just thought we'd talk about these 4 points. So we're going to talk about transforms, and we're going to talk about the Kutta Jokouski theorem and the Kutta condition for airfoils. The reason I'm talking about these 3 points is, remember guys, we've been talking about potential flow around ovals and circular cylinders. To be honest, that's not of interest to us. We know what we want is the flow around airfoils. And to do that, we need to talk about all these 3 things, as you will see. So this is really just to show you how potential flow can be applied to airfoils, which is what we want. Okay? And these are the things we will cover roughly. So it's a very short part of the lecture. So just to start, as I told you, aerospace engineers, we are more interested in flows around airfoils and wings. The problem is, with potential flow, is that an airfoil is actually a complicated geometry to model. So if you try different combinations of sources and sinks and vortex flows and uniform flow, it's impossible to get realistic shapes of airfoils. It's just not possible. You can do it with circular cylinders and ovals, but with airfoils it's just very difficult. So what do we do? So what did mathematicians do to overcome that problem of modeling the flow around airfoils? So they came up with this concept of, it's really a mathematical trick called mapping. And what they do is, they solve the flow around a circular cylinder, and then they map it so that it actually represents a flow around an airfoil. And in that sense, we get the flow around the airfoil. Okay, is everyone clear? So you just use that. Just think about it. The simplest way you can think about mapping is, we all know the Cartesian coordinate system, right? And we all know the polar coordinate system. They are the same, but just one of them is a map of the other. Okay, you can use either one. In terms of what they give you exactly the same answer. It doesn't matter which axis you use. This is exactly the same idea. So I looked at last year's notes, and I think Sean, bless him, he put a lot of effort into extra time to go through derivations and stuff, but we don't have time for that this year. All I need to tell you really is that we go from one complex plane called Z, we know that, to another complex plane, probably you haven't seen that before, called zeta plane. Okay, and we just map solutions from one plane to another. I'll show you what I mean. So here is one famous transformation or mathematical trick. It's called the Jokouski transform. I don't want you to worry about that equation at all. Just understand there is something called Jokouski theorem, transform, which allows us to do this mapping of solutions. So it says that the link between the complex plane Z, which is actually representing where the airfoil is, and another complex plane zeta, which represents the flow around the cylinder, is just written, this is how they are linked together. So Z for the airfoil equals zeta plus some length square divided by zeta itself. And actually by changing the value of L, you can get various shapes of airfoils of various thicknesses and trailing edge sharpness. Okay? But the whole idea of this transform is to go from flow around the cylinder, which I can solve using potential flow models, to a flow around an airfoil, which I can't do with potential flow. I have to do this transform. Okay? Is everyone clear? This is the key idea. So doing this, we get clearly, because Jokouski did this, so he called all the airfoils he generated his Jokouski airfoils. One thing about these Jokouski airfoils is they're usually very thin. They also have very sharp edges. So they're very specific in that definition. But you can make them slightly thick as well. But definitely they're normally quite thin and a sharp trailing edge, which obviously might not be suitable for some applications. You might need to think about that. But this is what this transformation is. Of course, people came after Jokouski and they introduced other transformations that you guys can read about. And they all do the same. They go from a flow around the circular cylinder to try to represent flow around an airfoil. And if you read textbooks, if you have patience enough to go through the pain of the complex analysis, then you can see there are quite a few transforms. And I thought I'll give you this picture, which I stole from the NASA website, which actually shows you, now we want an airfoil, we want a lifting flow, right? We want the lift to be generated. So the picture on the left is what we did before. That's the potential flow around a lifting cylinder or a rotating cylinder. So as before, there is flow asymmetry, top and bottom. Therefore, I know there is a lift, okay? And the stagnation points as before at theta equal to 0 and theta equal to pi. So that's fine. We can do that with potential flow theory. We can't do it with airfoils. So this trick maps this solution to that solution. Yeah? So it just, and it all does it mathematically. So we get this solution about an airfoil. So actually, the cylinder becomes an airfoil, and you get two stagnation points for the airfoil, one at the front, which actually that's true, and one at the trailing edge. And also, do you guys think this is a lifting flow solution about the airfoil or not? It is, yeah, because it's flow asymmetry, and definitely there is a lift about the airfoil. So that's it. That's the trick they use. And as I said, it's very complicated, the maths itself, but this is the key idea: is mapping flow solutions that we can do to flow solutions we can't do around airfoils. Right, let me just check the time. Yeah, not too bad, we can finish these ideas. Okay, so let me just remind you that for a lifting cylinder or a spinning cylinder, we found that the lift per unit span, I should have said that before, well, it's 2D, we know it's per unit span, is given by the Kutta Jokouski theorem. So lift is density, free stream speed times circulation. Okay, so the good thing about this is that we can actually remember we're dealing with the potential flow. There is no boundary layer, but at the same time we can actually calculate the lift, which is actually great, isn't it? So I'm getting the lift, I'm not modeling the boundary layer, which is great. Do you guys think this is a good thing? You can actually get a lift value without worrying at all about the boundary layer. And that's through that theorem, okay? Now, let me ask you a question. Does that mean we don't need the boundary layer to get lift? What do you guys think? That's an interesting question, isn't it? So this theory says, from potential flow, that's my lift. Okay? So as long as I know what the circulation around the airfoil is, somehow, we can get my lift. And there is no consideration of the boundary layer. So let me ask you a question. Do we need the boundary layer to get the lift? Yeah. Yes, we do. Okay, so the two things, we can discuss this at some point, but saying this doesn't mean we don't need the boundary layer to get lift. If you don't actually have boundary layer, there will be no lift, trust me. But at the same time, you can get lift without modeling the boundary layer. So that's there. So don't confuse the two things. So this equation, as I told you, is independent of the 2D shape. So it can be any 2D shape, including cylinders and airfoils. We're more interested in airfoils, of course. Of course, it only gives us lift. The drag is 0 as before, D'Alembert paradox, so we can't do anything about drag. The only way to get drag is you have to have a model of the boundary layer. Otherwise, you get 0 drag. Right, from the equation, so density times speed times circulation. Clearly, if circulation around the airfoil or wing is 0, you get no lift. If you think about it practically, if someone designs an aircraft which doesn't generate circulation, would it be a good idea to board that aircraft? No. So please don't board an aircraft with 0 circulation. Okay, it has to have its circulation. Okay, now, I told you before that depending on the value of circulation, you get a different value of lift. And what we've seen for the circular cylinder, the lifting circular cylinder, is we get an infinite number of solutions depending on the value of circulation. It's exactly the same for airfoils. We can get an infinite number for a given condition of rho and u. If you just change the circulation, then you'll get a different lift. But we know for a given condition, there's only one value of lift. Is that correct? You guys follow? Yeah, if I want to calculate the lift around an airfoil for given conditions of density and speed, we know there's only one value of lift, right? For a given condition. Not many values, it's only one value. The problem with that equation says, if I just vary the value of circulation, I can get an infinite number of lift, which of course doesn't make sense. It gives us like an undefined problem. which brings us to the conclusion that there must be a condition that we need to enforce on the value of circulation so that that lift value is one single value for a given condition, all right? And that condition is called the Kutta condition. So what is the Kutta condition for a flow around an airfoil? Is the condition that fixes the value of circulation so that for a given condition of a free stream flow with UN density, we have only one value of lift as expected, not infinitely many lift values. So that's called the Kutta condition. So let's talk very briefly about the Kutta condition. Really, what is the Kutta condition? It says the following, that for a flow around an airfoil, we have to have this condition that the flow must leave the trailing edge smoothly. Meaning, for example, I can't have the case where, let me just demonstrate this, sorry. With the second example here, for example, you guys can see here the streamlines from the bottom, they go around because they can do anything, right? If you're not putting conditions on the flow, you can create any flow picture. Now, this is actually not realistic because this actually, what it means here is actually you might get like an infinite velocity, which we know is not true. For example, in this case, okay? So, what the Kutta condition said, Mr. Kutta, I think he's a German mathematician, Martin Kutta. So he said that to fix the value of circulation and therefore to fix the value of lift, the flow at the trailing edge must leave smoothly. So when you think about it, okay, what do you guys think about the flow leaving at the trailing edge smoothly? In terms of velocities, what do you think that point is? If something is leaving smoothly, what do you think that point is? Or okay, what do you think the speed is there is? Yeah?
It's flow separation.
No, exactly at the trailing edge, not after. Okay, think about it this way. There is a flow coming from the upper surface, and there is a flow coming from the bottom surface, and they meet at the trailing edge. For the flow to go smoothly, what do you guys think at the point when they meet? What's the total speed, do you think? Yeah, but they're coming from different, one is from the bottom, so they cancel each other out. So the total speed at the trailing edge will be 0, right? What do we call the point where the speed is 0? Stagnation point. So, what the Kutta condition says, the flow must leave smoothly at the trailing edge. As your friend said, that means the flow coming from the top with the speed, let's say u1, and the flow coming from the bottom speed u2. Those speed at the trailing edge must be equal. But because they're coming from like 2 different directions, when they meet exactly at the point of the trailing edge, they will cancel each other, and we actually get stagnation point, which allows the flow to leave smoothly. And by doing so, we're fixing the value of circulation, and therefore we are fixing the value of lift. So this is the key concept of the Kutta condition, all right? Anyone has a question about Kutta condition? Do you guys understand the Kutta condition? You're looking at me, no? You understand it? Okay, good. It would be helpful to nod, because you're just looking at me. I was like, I don't know. Right. So this is the Kutta condition. The flow leaves with the trailing edge, which fixes the value of circulation to get the lift. That's what it is. I'm not going to repeat myself. From that theorem, you can also show that the lift coefficient, the gradient of the lift coefficient curve is 2 pi. Do you guys remember this? Does it ring any bell from last year? Yeah? We did this last year. We said from airfoil theory, I didn't tell you it's that theory, the slope of the lift curve CL versus alpha is 2 pi, exactly 2 pi. And that actually could be derived from the Kutta Jokouski theorem, which is L equal rho u times circulation. And what this really says is, doesn't matter what the airfoil looks like, then the lift curve slope is always 2 pi according to that theory. So you always know it. So obviously, you can work out the lift coefficient at any given alpha by just multiplying 2 pi by the alpha. That will give you the lift coefficient. So this is the lift coefficient curve slope. So I hope you can see the link between the discussion we had with circular cylinders and the discussion we just had for airfoils, and you can see how some of the concept link with each other to get to what we want, which is the airfoils. Okay, let's have a summary for this. Right, so conformal mappings or transforms, they give us the ability to describe potential flow around 2D airfoils. The reason being, it's very difficult for potential flow to model flows around airfoil shapes without this transformation or mapping. So we have to use that mapping. One of the famous ones is the Jokouski mapping, okay, which creates the Jokouski airfoils, which are usually quite thin, and they have a sharp trailing edge. And basically what you do, you start, if you want lift around an airfoil, or you create an airfoil with a lifting force, then you start with a flow around a cylinder which is a lifting flow around the cylinder. You map it to a flow around an airfoil which produces lift. The value of that lift for any shape, including airfoils, is given by this equation, where capital gamma is the circulation. So clearly no circulation, no lift. But remember, the drag is always 0 according to potential flow, which obviously is nonsense. So we have to model the boundary layer. And then we said that for given flow conditions, we need to fix the value of circulation so that we have a unique value for lift for given conditions. We know it's only one value. And that's enforced by the Kutta condition. So the Kutta condition says that the flow around the airfoil must leave smoothly at the trailing edge. Okay, which really means that the trailing edge itself is a stagnation point, meaning the two velocities meeting at the trailing edge cancel each other and the flow leaves smoothly. And that fixes the value of circulation, gamma, capital gamma, and you get a unique value for lift. And remember guys, no circulation, no lift. Okay, so if Joe designs, I don't know, sorry, can I use you as an example?
You already have.
So if Joe designs a wing which has no circulation, please don't get on that plane using that wing, okay? So that's, and I think that's final, if you, okay, can anyone tell me which flow picture is real? What do you mean second? Which one, left or right? On the right. Why is that? Just one person, please? Who's talking here? Yep. Very good. Yeah, so the flow picture on the right is the correct one, because on the left we can't have flow not having stagnation point at the trailing edge. That is basically Kutta condition saying the flow must leave smoothly at the trailing edge. So that's the correct flow picture. That is not a correct flow picture. Okay, so this is the correct one. So try to use these ideas when looking at flow pictures next time and thinking about lift and drag. Right, thank you guys.